Time is up and we are starting this webinar. I would like to give a warm welcome to all of you for this first episode of 7N webinar. What can organizations learn from space exploration? My name is Thijs Eichel, and I'm a VP at 7N. And with me today, I have Anja. And Anja will give us some insights and hopefully also give us the ability to get a bit wiser on space exploration. But instead of me talking about what it is all about and introducing you, why don't you self-introduce you?
I'll be happy to do that. Thank you very much. So thank you to all of you who are out there. So my name is Anja Andersen. I'm a professor at the Niels Bohr Institute at the University of Copenhagen. And my research area is interstellar matter. So I'm an expert in dust. And you can imagine the many jokes that I hear at a workplace, which is mainly male, that the woman is studying the dust and all the dust belongs to the women, and it's difficult for women to be interested in dust. But the reason that dust is so interesting is actually that interstellar matter matters. So if you look at the Milky Way that you see here in the sky, then all the dark patches that you see, that is actually gas and tiny dust grains which are hiding the stars in the Milky Way, so we can't see them. So if we had no gas and dust in the Milky Way, we wouldn't be here because there would be no Earth, there would be no life. But also the Milky Way would be 1 billion times brighter in the night sky. So instead of being difficult to find, it would just be a really, really bright patch on the night sky. So just to give you an idea, what does it mean to be a researcher? What does my work look like? So even though I have my sort of head in the sky and I study with telescopes, then because I study dust, I also do laboratory work where we look at dust analogs, we look at dust from meteorites, where we try to understand what's going on. So here's a picture of one of the laboratories that I work in with colleagues in Germany and Jena. I am at the PSI, Paul Schiller Institute in Switzerland, doing experiments on dust. Then there's my office where I write on the backboard with the students and try to find out what it's actually all about and what we measured. And then, of course, when there's no COVID, I go to international conferences and interact with my international colleagues, which unfortunately now is all on Zoom, but hopefully we will be able to travel at some point soon in the future. So as an astrophysicist, we use different tools. So we use telescopes that we have on Earth, but we also use satellites which are outside the Earth atmosphere. And then we're very dependent on computers because we get our data down on computers. So we analyze our data on the computers, but also we do numerical models and we analyze all our data and we try to understand what we see. And that's what I'm going to do in this webinar. I'm going to try to bring you along on a journey where I introduce some different topics and try to explain to you how do we go about these topics and what is it actually that we study and how do we study it. So the first annoying thing when you're an astronomer is that we are on Earth and Earth has an atmosphere, and the Earth atmosphere means that it is actually not transparent to all the light, because astronomers, we're very inclusive. We love all wavelengths. So for us, everything which we call the electromagnetic radiation is light. So that means gamma rays, X-ray, ultraviolet, optical light, infrared, microwaves, and radio waves. They are all light for an astronomer, but unfortunately the Earth atmosphere that you've seen sort of pictured here above the electromagnetic radiation, and then it is shown where the Earth atmosphere is not transparent. So that's sort of the white stripes that you have. And then you can see there's like a visual window, an optical window, and a radio window. And that is actually why we have telescopes on Earth. That is actually because that's one of the few wavelengths that actually can make it down through our atmosphere, and that's probably also why our eyes are designed to see these wavelengths, because that is actually what we can hope to see. But as you can see on the optical window, that if you go up 3 kilometers up to the top of a mountain, then the optical window is a lot broader and you actually get more information if you move up. And that's why we like placing our telescopes on the top of mountains, because then we get twice as much information as we do when we're standing down at the surface of Earth where Denmark is. Then we have the radio window where we have our radio telescopes, and then we have satellites which we need to use to see all the other wavelengths. So Denmark is just a small country. We cannot afford to have lots of technical equipment of the you know, in astronomy, size matters. If you have a big telescope, you just see more light because you have a bigger mirror. So luckily, Denmark joined the European Southern Observatory in Chile with the other European countries, where we have 4 different mountaintops where we have telescopes. So we have Lasil up in the upper right left corner, which was established in 1975. Then we have Paranal, where we have the very large telescopes that was established in 1998. And then we have what we call ALMA, which is 64 radio telescopes, which was established in 2011, and they are at a height of 5 kilometers. So they are up so high that it's actually very difficult to go observing with them because you get altitude sickness. And then right now we're building a really big telescope. And so as we already used the name Very Large Telescope in 1998, we call our new telescope Extremely Large Telescope because it's 39 meters in diameter, and it should be finished in 2024. And just to give you an idea of how far we are in the process, then here's the building site. So the telescope is not quite there yet, but as you all know, if you have a good foundation, then your building is basically almost already up. So here you see we still expect it to be on time despite COVID. So we expect to have the big eye at the sky 39 meter telescope ready in 24. Then we have access to a whole fleet of satellites. And that's also thanks to a European collaboration where we're part of the European Space Agency, which actually has a whole fleet of different satellites, which are specialized at the different wavelengths that you cannot see from the surface of the Earth, but you can see from space. So we have access to all of this thanks to international collaboration. And what we are really excited about and waiting for in astrophysics at the moment is the James Webb Space Telescope. Because right now we have the Hubble Space Telescope, which is more than 30 years old. You see it to the right. It's a 2.4 meter telescope. And the James Webb, which is going to be launched in November this year, is going to be a 6.5 meter telescope. And 6.5 meter is actually quite a challenge because the engineers can build space shuttles or space rockets, which are only about 3 meters in diameter. So in order to put up a 6.5 meter telescope, we have had to develop a completely new technique where it's possible to fold the mirror so that it fits into the rocket when we send it up. And then the mirror has to unfold a bit like a flower when it comes up into space. So here you see how big the mirror is. You see the structure of the mirror, which makes it foldable. And then we really hope it works when it gets into space, because in contrast to the Hubble Space Telescope, which is placed relatively close to Earth, so it's in an orbit of about 500 kilometers about the surface of the Earth. And that has turned out to be a huge advantage because that meant that we were able to send astronauts up with the space shuttle to repair the telescope when it turned out that there was actually an optical mistake when we sent it off. So it wasn't quite as sharp as it was supposed to be, but that was fixed, and we have been able to upgrade it as time has passed by sending up astronauts. The James Webb Space Telescope is going to be sensitive both in the optical and in infrared, and infrared is heat. And since the Earth is very warm, we need to send it further into space. So we're actually putting it on the other side of the moon in a special point that's called L2, which is a Lagrange point where it's in a special dynamics with the sun and Earth. And that means it's going to be so far away we can't repair it. So it better work, because else we're going to be in big trouble. Just to give you an idea, so what is the development? So as I said, as we get access to bigger telescopes, if we get better techniques, as we get better at doing our work, we actually get to look further into space. So here you see a slide that illustrates that. So in 1990, we were able to look relatively far into space. And then the future James Webb that you see at the bottom, we expect to be able to look so far into space that we can look back in time, and we will actually be able to look all the way back in time to what we call the Big Bang. The reason that we are able to do that is actually because light is such an interesting thing, because light is little photons, so it's little light particles. And the Danish physicist or the Danish scientist Ole Rømer was the first to actually show that light spends time traveling from A to B. So there is actually something like a light traveling time. So there's the speed of light, and that means that light takes some time to travel from one place to the other. So that's illustrated here. So you can see if we want to look at the moon, then it actually takes like a little more than 1 second to go from the moon and back. So we know exactly where the moon is because we regularly shoot laser beams at the moon, which are reflected from big mirrors that the astronauts put up on the moon. So we know exactly where the moon is, and we know exactly what the light traveling time between Earth and the moon is. The light we see from the sun travels for 8 minutes. So that means if the sun stopped shining today, it would actually take 8 minutes until we realized that the sun was no longer shining. The closest neighbor to the sun in our own galaxy, the Milky Way, is Alpha Centauri, and that is actually at a difference of more than 4 light years. So that means when we look at that star, we see the light that it sent out 4 years ago. So we don't see it what it looked like today. We see it as it looked 4 years ago, and if we want to know what it looked like in this particular moment, we have to wait 4 years for the information to reach us. If we look at what is called globular clusters, which are big clumps of stars which are around the Milky Way, then light will travel for about 25,000 light years, which is also approximately the distance to the center of our Milky Way.
There we go. Sorry for the inconvenience. I think we are back on track.
Okay, I'm really, really sorry for the interruption. You know, it's difficult with internet, and sometimes it's amazing that we can actually explore the Big Bang and the big universe, and we can send astronauts to the moon when sometimes it's difficult even to get the internet going on Earth. What I was saying before we got so rudely interrupted was that, so because of the speed of light, the fact that it takes time for light to travel from A to B, that means that when we look out into the galaxy with our big telescope, or into the universe with our big telescope, then the further away an object is, the longer the light travel time has been, so the longer time has spent traveling down to us. And that actually means that we look back in history as we look out. So if we look a certain distance, we look out like 1 billion years. If we look a little further, we look 2 billion years back in time, 3 billion years, 4 billion years, 6 billion years. And by doing these observations, we have found out that actually the universe is not infinitely old. It has a determined age. That's what we call the Big Bang, that it seems that the universe started 13.7 billion years ago. And with the James Webb telescope that we're going to launch in November, we expect that our mirror is so big that we will be able to see the very first galaxies who are now very faint because the light has to travel so far before we can catch it, so that we see the first galaxies in the universe, and we can sort of confirm if the Big Bang model is real or not. When I talk about the Big Bang model, it sounds like there's one model that all astrophysicists agree on. Actually, the Big Bang model consists of something like 120 different models, but all the models, which are sort of theoretical models verified by computer models, have that one thing in common, that they all believe that the universe was smaller and hotter and more condensed, and then it's been expanding. But you can do that in many different ways and still be in accordance with math and physics. So exactly the details of how that is, we don't know. And that's why we have competing Big Bang models. And what James Webb is going to do is it's going to see what it's really like. Then it's going to kill approximately, hopefully 40 or 60 of these models, so that we only have half of them left. And then we have to try to find out which one holds the truth, so to speak, which one measures up best with what we can observe. So just to give you a flavor for what is it we can see when we as astrophysicists uses different techniques and different observing techniques and look at different wavelengths. So here you see an interstellar cloud from our own galaxy, the Milky Way. It's called the Eagle Nebula because some people think it looks like an eagle that's flying something like this through space, especially if you look at it in a small telescope. And this is the Eagle Nebula as it looks if you look at it in an optical telescope. So this is what you can see with your eye. So if we zoom into the center of the Eagle Nebula, where you see sort of the white triangle, and we use the Hubble Space Telescope to zoom in and we turn it 45 degrees, then we can see that in the center of the Eagle Nebula, then there is these, we call them pillar of creation, because you have gas and dust. And it's from this gas and dust that you form new stars and new planets. And just to give you an idea how big this structure is, then if you can see the little square, which is now in the middle, I'll blink it a bit so you can see it, then this is the amount of gas and dust you need in order to create the sun and all the planets in the solar system. So that means that from this structure, we expect a lot of stars can form and a lot of planets can be formed, which is sort of similar to our own solar system. This is what we see when we look at this part of the Eagle Nebula with optical telescopes, when we see what the eye can see. If we use a satellite, which can see heat radiation, so we look at it in what we call the near infrared, which is a wavelength that the eye cannot detect, then the same area of the sky looks like this. And this gives you an idea of why astrophysicists really want to look in different wavelengths, because if we use different techniques, we get a better overall view of what is actually happening. It's like looking at things from different angles, and we can only look at it from one angle, right? Because we're sitting on Earth looking into space, and space is always directed in the same way to us and not much is happening. But by looking in different wavelengths, it's equivalent to getting different bits of information. And we can see there's actually a lot of stars in this part of the sky, which seems to be basically stellarless, because the interstellar clouds actually block the light. And you can see that these pillar of creations are actually maybe not creating quite as many stars as we thought. They're actually a little sparse, but there's still material enough to make quite a few solar systems, but maybe not as many as I indicated by looking just in the optical. So when we look at the Milky Way, our own galaxy, because that's astrophysics is very much finding out what is the origin of space, what is our place in space, what is the sort of the meaning of everything. Then we look at our Milky Way, we see it as a stripe of stars on the night sky, and it's sort of these patterns of gas and dust. And then if we sort of zoom into it, so here's a small video which is made from Hubble Space Telescope, where we zoom into a specific part of the Milky Way, and then as you get closer to all the dark patches, that there's actually little bright parts of the dark patches, which is sort of in shape, and these are the areas where we just have new form stars, and these new form stars that form inside the dark clouds, as the stars form, it starts shining, and when it starts shining, it blows away the cloud, and then it gets out in the universe where we can actually observe it and we can see it. And hopefully by now you can see that we're zooming into the Eagle Nebula. So this little video is just to show you that the Eagle Nebula is actually part of the Milky Way, and it is something that you can go and observe on the night sky. If we look at the Milky Way with all the different techniques we have, so all the different satellites, all the different telescopes, so radio telescope and optical telescopes and gamma ray satellites, then this is what the Milky Way look like. So this is what the Milky Way is in all the different wavelengths. So if you look at the sort of the two bottom ones, which is called gamma ray and X-rays, then X-rays, that's equivalent to what Superman would be able to see if Superman went out and put on his X-ray vision and looked up in the night sky and looked at the night sky. And that's of course not quite true, because if Superman did that from Earth, he wouldn't be able to see anything, because X-rays cannot go through the Earth atmosphere. So he actually has to put on his cape, and then he has to fly into space like a satellite and be outside the Earth atmosphere, and then this is what he sees. So the two bottom panels shows you gamma rays and X-rays, and the radiation we see there, we believe, is from what astronomers call dead stars. So it's from like black holes and white dwarfs and neutron stars. And then we have what is called optical. So that's what the eye can see and normal telescopes can see. And here we see the light from what we could call the living stars, the stars as the sun, which is shining. And then above that, you have three panels called near infrared, mid infrared, and infrared. And what you see there is the heat radiation from the little dust grains. So the dust grains don't shine, of course, because they're just little specks of dust. So they're like sand that you find on the beach, or the little coal you find inside your barbecue after you have been having a barbecue. So it's just a really little aerosols, basically. So they don't shine, but what happens is that when the stars shine at them, they get warm, and we see the little heat glow from the dust grains. So that is actually where we can learn something about the dust that is in the infrared. Then above that, you have 4 different panels, which are all done with radio telescopes. And what the radio telescopes can measure is what we call the gas. So that's like atoms and molecules. So all this is maybe a little technical, but the idea is just to give you a feeling for, that means the top panels tells us the Milky Way is full of gas. Then we have 3 panels saying there's lots of dust. And then we have 1 panel saying that there's a lot of living stars. And then we have 2 panels saying there's also a lot of dead stars. And that's what we know about our galaxy. But we really would like to know, if we were not sitting inside the galaxy, but could see ourselves from the outside, what would our galaxy look like? So the next image here, that is actually a model. That is our best estimate of what would the Milky Way look like if we could fly out of it and take an image. And then you wonder, why don't we just do that? How difficult can it be? You send up a satellite, then you fly out and you bring your mobile phone, you take a selfie, and then you want to know what the Milky Way is. But the problem is that the galaxy is very, very big. So the little yellow pads, that's where we believe the sun is situated in this model of the Milky Way. And actually all the satellites that we send up, so Pioneer 10 and 11 and Voyager 1 and 2, which have left the solar system, is within the little yellow circle. So it would take actually billions of years for any of these space missions to get out and actually be able to take an image of the Milky Way. And since they were all built in the 70s and the technology in the 70s weren't quite as good as my iPhone, then we can't really get an image. So this is our best guess of what the Milky Way looked like. So as you can see, the sun is sort of away from the center, and the distance between the sun and the center is 25,000 light years. So that means that when we look at the stars in the center, we believe that we see the stars as they look for 25,000 years ago. The sun is moving around the Milky Way. All the stars are moving around in a sort of a circle or an ellipse. And we believe it takes something like 216 million years to do one orbit. And that means that since the creation of the solar system, our best estimate is that the sun has been 16 times around the center of the Milky Way. You can see that the Milky Way also, we think that it has some spiral arms, and you might think, why do we think that? Because why do we think that it has spiral arms and the gas and dust is just not evenly distributed? And the reason we think that is because when we look out of the Milky Way, out at all the other different galaxies we can see, then most of them look like this. 75% of the galaxies we can see are spiral galaxies. Just a little bonus info. If you are in Denmark or in the northern hemisphere and you look up into the sky, then you actually look out of the Milky Way, like equal to looking down the image. If you are so lucky as to be on the southern hemisphere, so in Australia or South Africa or South America, then you actually look up the image, so you look into the center of the Milky Way. So those who are in the southern hemisphere, they actually see into the heart of our galaxy, into the center of our galaxies, while us who are up here on the northern hemisphere, we look out of the galaxy, so we don't have quite as beautiful a view of the Milky Way. But for an astronomer, that's very nice, because it means if we want to study our own galaxy, it's good to be in the southern hemisphere. But if we want to look out of our galaxy at other galaxies like the Andromeda galaxy, then we want to be on the northern hemisphere. So here you have the Andromeda galaxy, which has a distance of 2.5 million light years, meaning that light has traveled for that long. And when we look at Andromeda and the other galaxies, then 75% of them look like this. So they have like a flat structure, and they consist of gas and dust, and they have spiral arms. And what we know from the data we have of our own galaxy is that we live in a flat structure that consists of stars and gas and dust. So we look at all the other galaxies and say, we're probably one of those, you know, we're more likely to be one of those than the 25% other galaxies, which are more round and only consist of stars. So they are sort of characterized by not containing any gas and dust at all. So looking at the Andromeda galaxies in different wavelengths. So here you see optical up in the upper left corner. So that's what you can see with the eye. Up in the upper right corner, you see infrared, meaning the heat glow from the dust. So you can see how the dust is distributed. You can see the dust is actually what forms the spiral arm patterns that you see in galaxies. And then at the bottom to the right, you can see X-rays. And you can see that the X-ray seems to be concentrated in the center of the galaxy. And then what we do as researchers is that we sit down and we ask ourselves, why is there a lot of X-rays in the center of Andromeda galaxy? What is going on in there? What is it that is sending out all this radiation? The middle image, that's the X-rays put on top of infrared. And then if you take the X-ray and infrared image and put up on top of the optical up in the left corner, you get the lower left corner. So the lower left corner is somehow all the information the Andromeda galaxy is willing to share with us, while the upper left corner is the information that we would see if we only looked at it with optical telescopes. If you go back to the lower right corner where we have the X-rays, then the big question is, what is sending out the X-rays? And the best estimate, or our best answer to that, is we think there is a supermassive black hole in the center of the Andromeda galaxy. So let me explain to you what a black hole is. So a black hole is in many respects astronomers' ultimate nightmare, because a black hole was theoretically thought of as a thought experiment by some physicists who say, okay, if you have gravity, and gravity is this force that keeps me on Earth. It keeps the moon moving around the Earth moving around the star. It's what holds things in place. And gravity is also what prevents us from building really big space rockets, because if we want to launch anything into space, then we actually have to work against gravity in order to lift it up. That's why we need so much fuel. So the bigger the planet is, the bigger is the gravity, the harder it is to send up a rocket. So the smaller it is, the smaller the gravity, the less fuel we need to send it off. So people are thinking, okay, if it means that the bigger you are, the more the gravity, could you imagine that you could have so much gravity in an object that the speed you needed to lift from that object would be the speed of light? And we believe that nothing, due to Ole Rømer's measurement, can move faster than the speed of light. The speed of light is the highest speed that you can hope to acquire in the universe. So people are thinking, okay, if you have something where the gravity is so high that you cannot move away, even if you have the speed of light, then you probably have a black hole, because you have an object where nothing can escape. It can send out no light and can send out no information. It has a lot of gravity. That means that it can take in a lot of information, but it cannot give off a lot of information. And in that respect, as black holes are astronomers' nightmare, because what our tools are is that we have telescopes, and we have fancy telescopes, and we have satellite, and we can look in different wavelengths. But here we have an object which doesn't apparently send out anything. Then, being a physicist, it's all about trying to solve problems, right? So when you encounter a problem which is, okay, we have a problem, we have a black hole, we want to find out if they exist. They are situated in a black universe. Black on black can be really, really difficult to see. Is there any way we can hope to see these? This is where computer models come in, because then you can sort of build a black hole in your computer, and you can say, okay, let's put an imaginary black hole in the Milky Way, where we have a lot of these interstellar clouds of gas and dust. And let's study what happens if any of these gas and dust clouds come close to the black hole, so that they get affected by the gravity of the black hole and actually get sucked into the black hole. And another thing is, we think the black holes are probably rotating, because all the stars we see are rotating and they're moving around the galaxy, which is then sort of also rotating. And then you can say, why should the black hole be rotating? And then as a physicist, I would say, why shouldn't it be rotating? If everything else is rotating, I want my black hole to rotate. That's not against the laws of physics. So imagine you have a rotating black hole, you throw in interstellar clouds, then what happens is that these interstellar clouds, they situate themselves in an accretion disk, and then due to all the dust particles and the gas particles bumping into each other, you create a lot of friction, and that friction creates a lot of energy, and that energy is what we see as X-rays from the Andromeda galaxy, because in this disk you create X-rays. Then physicists, we like to play, right? So we just put in a lot of interstellar clouds, and we say, okay, how many interstellar clouds can a black hole of a certain mass actually swallow up, and how effective are they at swallowing up material? And it turns out that if you try to feed your black hole too intensely, then it will actually, the material will start interacting on the way into the black hole, because the black holes are actually quite small. So they will create jets that will send out radio wavelengths. So we have a model saying, okay, you cannot see a black hole, but if interstellar clouds are on the way, or a star is on the way into a black hole, you can expect to see X-ray from an accretion disk, or you can see radio waves from jets. So just to show you sort of a prettier drawing, which also shows that these jets are very narrow, like a hose, due to the magnetic field that happens in this material as it gets swirled around. So this is our working model, and this is actually an observation where we have two images on top of each other. So we have an optical image of a galaxy, and then we have a radio image of the radio jets we see from that galaxy. And we think, wow, that fits our model so nice. So we look at this galaxy and say, we cannot really see if there's a black hole in the center, but that's a very good prediction. There probably is a black hole that creates these radio loops that you see around this galaxy. Then, of course, if you think the Andromeda galaxy has a black hole, and you think Centaurus A that you see here has a black hole, then the obvious question is, what about the Milky Way? If we think our galaxy is like all the other galaxies, then the Milky Way must have a black hole. So, of course, we went out with our radio telescopes to look, do we have any radio loops? Do we have these jets that we can see in the radio? And there is nada, there is no radio jets around the Milky Way. Then we take our X-ray telescopes or satellites. We look into the center of the Milky Way to see, okay, is there any X-ray radiation? There's no X-ray radiation, right? And then you wonder, okay, what's going on? Is it that the Milky Way doesn't have a black hole? Is our model wrong? Is it that not all galaxies have a black hole? What's going on? And then there were some ingenious researchers who said, okay, if there's a black hole, then we'll only be able to see it if it's actually interacting with interstellar clouds. Imagine that there's no interstellar clouds in the very center of the Milky Way, that somehow the black hole cleaned up somehow, but we still have stars moving around. So can we maybe, by observing the stars in the center of the Milky Way and how they move, infer from their movement whether there's a black hole? So that seems relatively simple. You take a telescope, you look into the center of the Milky Way. The problem with looking into the center of the Milky Way is there's a lot of stars in the center of the Milky Way. So you get sort of so many stars that it can be really hard to tell one from the other. So just to show you that actually in order to do this and find out whether there was a black hole in the Milky Way, then we need to develop some new technology. So here you see the center of the Milky Way, where the little patch shows you when we don't use what we call adaptive optics that I'll explain to you in a second, and then what it looks like when we do use adaptive optics. So if you look inside, you can now see that we go from adaptive optics off till on. So we get a much better image of what's going on inside the center of the Milky Way by using adaptive optics. That's hard to say. So what is that actually? So here you see two telescopes down in Chile, and they're sending up little laser beams. And the laser beams has this function that they create a synthetic star on the sky, so that you get a little star formed in the atmosphere of Earth. And then you can see how much that star flicker, so that you know how much turbulence do you have in the air from Earth. So if we look at a drawing, it looks like this. So if you see Earth is the green thing, then you have a telescope on Earth, you have a satellite, which is outside the Earth atmosphere. They're looking at the same star. And as you can see, the radiation from that star is sort of drawn as parallel lines. So that is like the light that we observe. And the satellite receives that light completely undisturbed. And the light from the star that goes to Earth is completely undisturbed until it passes through the Earth atmosphere, where due to wind and turbulence in the Earth atmosphere, it gets like a wavy structure. And the idea of adaptive optics, is that you can actually unwiggle your light so that you can get the parallel sort of undisturbed light out of it. So what happens is that you have these mirrors, which are very, very thin, and then you have little legs sort of controlled by computers underneath, which can completely distort your mirror so that it can compensate for the wave front that you get from the light, so that the light that you then get into your detector is actually parallel light, almost as good as if it was observed from space. So just to show you an image of the planet Neptune from our own solar system, used with not using adaptive optics to the right and then using adaptive optics, you can see we get a lot more detail just from making advances of having computer technology, being able to deflect our mirror and having very effective mirrors that we can actually control on the nanosecond scale level. So looking into the center of the Milky Way, we were trying to find out, is there a black hole in the center? Once we had come across adaptive optics, it was possible for us to actually find out how do the stars move around. So in order to do this type of research project, you have to be very patient. So here you see some data from the research paper, and you can see that the data started in 1995, and they are still observing, but this is the data from 1995 to 2012. And you can see that then they went out, they took an image, and then 6 months later, they came back, took a new image, and 6 months later, took a new image. And then every time they went back to their offices, they put it into the computer and they tried to find out how had some of the stars moved between the image that they took 6 months ago. And then they dotted in the little dots, and they saw that the dots moved in certain orbits. And then we can use Kepler's law and our understanding of gravity to actually find out what is the true orbits of these stars. And actually, with the inner stars, they are almost having a full ellipse. And then we get very excited, because if we have a full ellipse, then we have the math that can actually infer how things move. So just to show you an animation, which shows exactly the same as the still picture that I just showed you. So if you see, you have years running up in your upper left corner. So here the data starts in 1992, and then you have like 12 years of measurements. And you can see that the inner star actually forms an ellipse, and all the yellow dots is then the images that we're taking with approximately 6 months apart. And the red cross, that is where we think that the black hole that we are certain is in the center of the Milky Way is, because that fits with why the ellipses and why the stars in the center of our galaxy move the way they are. So our conclusion today is that yes, we do actually have a black hole in the center of the Milky Way. It's just dormating, as we call it. It's sleeping because there's nothing going on in there. None of the stars are close enough that they are likely to encounter with the black hole at this time. So there's no gas getting sucked into the black hole that would give us X-rays or give us radio loops that we can observe. Just to show you the data again. So here, so the red star is the one that we were excited about because that was what gave us the mass of the black hole. And the black hole in the center of the Milky Way is 4.1 million solar masses. So we have something in the center of the Milky Way that weighs 4 million times what our own sun weighs. And it doesn't shine. It doesn't send out any radiation in any wavelength. And the only good idea we have what that could be is a black hole. So because we are so certain, and because we have managed to convince the Nobel Prize Committee, then these 3 people got the Nobel Prize for actually predicting or showing that the Milky Way contains a black hole in the center. So these are the 3 happy laureates from December last year. We have also seen black holes, and we actually have managed last year to get the first image of a black hole. So here they used different radio telescopes. So the little globe that you see, Earth, it is actually shown that the yellow dots are different radio telescopes. And if you use radio telescopes positioned in different places on Earth, then you can actually get them to work together in what we call interferometry. So they act like they're one big dish, like they're one big telescope. So you can see in the last image over at the right in 2017, we actually got so many radio telescopes to work together that we got such a much better image of the black hole in the galaxy called M87, which is a nearby giant galaxy to the Milky Way. So here you see several images on top of each other. So there's an image of M87, which is the galaxy that you see, and then there's a zoom in where you see that this galaxy actually does have 2 radio loops. And then there's a zoom in again, which shows that you have this disk of glowing matter around the black hole on its way to entering the black hole as it crosses what we call the event horizon. And just to give you an idea of the data that we work with, so here's some observations where you can see that we're zooming into the radio loop. So every little square here shows you that you zoom in more and more into your data until you actually get the actual image of the black hole in M87, which is actually the first time that we have seen an image where we actually see a black hole. So now we are absolutely convinced. If we weren't convinced before, we are now convinced that they do exist. So these are drawings of models, of computer models, trying to then look at the image which you have in the middle. And then you have 2 computer models saying, okay, what can we learn from the details? So there are some little structures that you can see in the observations, and they're not very clear, but we think if we can model them on the computer, then we can understand better what happens and how black holes actually sculpt up all these material, which is on the way into the black holes. So just to give you an idea of the size of this black hole in M87. So here there's a little sort of drawing of the solar system put into M87. So you can see that this black hole is actually bigger than our own solar system, but it's not bigger than Voyager 1 that was sent up in the 70s and had left the solar system. It would still be sort of inside the black hole. So it's relatively small on an astronomical scale, but of course relatively big on a human scale. So it's a big black hole, but it's actually not that big compared to other sizes in the universe. The reason we were so excited about these observations was because they once again indicated to us that Einstein's general relativity was actually true, because black holes was something that sort of dropped out naturally as a consequence of Einstein's ideas in general relativity. He didn't quite believe it himself. It actually took some years for other physicists to convince him that was actually part of his theory. And his theory was trying to explain what gravity really was, and what he shows was that gravity actually bends space and so that space and matter or mass is somehow connected. So if you have something that has a high mass, it curves space. and that space actually curves around things that has a mass, and that influences the way that light travels in space. So it's something that we as astrophysicists have to be very much aware of, and we were super excited that we actually had yet another proof that Einstein's general relativity's prediction turned out to hold up. That actually, you know, one thing is that he has a prediction, another thing is that it actually fits the measurements that we can do when we can do really advanced measurements. So with that, I would like to end this talk and then pass on the floor to Thijs, or invite him up so we can discuss a little. And I would say, if any of you have any questions, I think if you write them in the chat, then you can get some answers.
Wow. And yeah, it's, you know, I hope that you understand that it's maybe a bit difficult to cope with all of this when it's not your daily work, right? So I asked you the other day, working intensively with these matters, do you ever get a bit afraid of the whole thing?
Yeah, so I mean, so one gets sort of a little dizzy, I would say, when you think about how big the scale is and how big the numbers is and how big the distance are, and the time scales are completely different from, you know, I can hope to live maybe 100 years, and then the Milky Way is like 12.6 billion years old, and the universe is 13.7 billion years old. And then you think, what is the meaning of my life, which is such a short time scale compared to the universe?
Exactly.
And that can be, yeah, it can be a little scary, but at the same time, it fascinates me that we're part of this very big sort of cosmic cycle, that we are here now in the galaxy, and there's a lot of other planets. We have actually discovered 4,000 planets around other stars. So which might also have a life, maybe not. So I actually find some comfort in the fact that the universe is so big, because somehow it takes a little responsibility of us, because if we don't do our business well, I'm sure the universe will survive anyway. There might even be life somewhere else that might be a little smarter than we are. But I hope that that we will act in a good way, in a proper way.
Well,
I mean, so far we've been a very successful species, I would say, on Earth.
Yeah. Actually, you led me to another key question, I think, before entering my presentation, and that's, do you believe in life outside the Earth?
I would be super surprised. So, I mean, we only know there's life on Earth, and we have looked for life on Mars. We have looked for life in other places. Recently, there was a research article showing that they observed phosphine on Venus, and we were all excited because phosphine is something that's related to life on Earth. It turned out that there was a misinterpretation of the data, so it was so there's no phosphine on Venus once we looked again, unfortunately. So we're all very excited. We would like to see life somewhere, and we are starting to have good enough techniques that we can find Earth-like planets. And some of these planets have atmospheres, and we don't know yet if they're like Earth atmosphere, but I would be very surprised if there's not life. Whether they're like you and me, or it's just little bacteria or COVID virus or something, I don't know.
Could be anything.
Or anything more exciting than you and me, that time will show. But there must be life. It would be really strange. It would be a big waste of space.
Maybe to roll back to our own globe.
Mm-hmm.
So
one more question.
Yeah.
How much of the Milky Way have we mapped percentage-wise? Would you?
Yeah, so the Milky Way, currently we have a satellite called the Gaia satellite, which is measuring 1 billion stars in the Milky Way with extreme accuracy. So that means that we know 1 billion stars extremely well in the Milky Way. We know where they are, we know how they move. We think the Milky Way consists of 200 billion stars. So that means we have mapped about 0.5% of the Milky Way in detail. And then we have mapped more of it in much less detail, right? So I would say we're still a bit fuzzy in our view of our own galaxy. There's work for many students to come.
I guess so.
And then we have a question in terms of the amount of data. How do you know what to look for? I mean,
oh, that's a super good question. So the question is, how do we know what to look for in the huge amount of data? Because we have like billions of stars in a galaxy, we have like billions of galaxies. So how do we actually keep track of the data? So we use machine learning and AI and all the different tools that one can do on a computer. But I mean, of course, that we are only as smart as our question, right? Because we ask ourselves a question when we look into our data. We ask like, is there black holes? And then we try to find evidence for black holes. And then we find evidence or no evidence for black holes. But there might actually be a lot of information in those data that we overlook because you find somehow what you're looking for, right? So the question that you ask is the question that you can hope to get answered. So asking good questions and asking lots of questions is quite important. And asking good questions are really difficult because it's very easy to ask like very big, impossible questions like, are we alone in the universe? Actually asking a question which is a good physics question, which is one that can always be answered with yes or no. That's much harder. So that's why we are actually not looking for life on Mars. We're looking for the existence of liquid water because we think we need liquid water in order for life to be able to have created itself and exist. And we know what liquid water looks like. And we can recognize liquid water when we see it. We don't know what life might look like if it looks different from us. So we don't know what to look for. So so somehow it's a bit sad because you only find what you're looking for. And then occasionally we're lucky, right? That we bump into things out of the blue, but most of the time we only find what we're looking for. You have to ask the right question. And I guess that's the same in a company, right? If you want to find out what's going on, asking questions, that's the trick, right?
Exactly. So I think with these words, Anja, I would like to thank you very much. This is the first session in a series, so we'll meet again.
Yeah.
Thank you for now so much. I'm a bit dizzy now, so I don't know about all of you, but it's fantastic and amazing. So I want to just give a couple of words on why we have created this seminar together with Anja. And that is because we think that you as scientists are on the very verge of what is possible when it comes to data handling, when it comes to finding out how to work together. And especially in these times, I mean, what is really difficult, I imagine, is to find out how you, in an easy way and accessible way, can work with people all around the globe and still have progress and control over what is going on. So that is actually what I would like to speak a little bit about, how we see that. So one of our main competences are data-driven IT advisory, focusing on optimizing your overall performance of your IT organization. We do that by asking the right questions to increase performance optimization and mitigate risks. Especially also in these times, I mean, it's extremely important to be aware of your risks, both when it comes to your IT development, your way of driving your business, etc. So the performance optimization as such, it's about asking the right questions, just as Anja stated, and to focus on finding then the right answers to navigate after. So it's the questions we normally challenge our clients with is how can we together accelerate the team productivity? How can we boost the efficiency in their organization? And how can we increase the quality of their products, their tech stack? So how we go about it is that we offer objective and data-driven advice by enabling technology throughout our delivery model. And as 7N as a whole, across the span of what we do, we see a lot of potential issues or risks but also substantial gains. I think that's a nice anchor to your speech, Anja, that also here on Earth we can see that those gains. So the future is characterized by digital products and services, and that are delivered through modern core architecture, digital platforms, and agile fragmented organizations. But as we see it, the future is not here as yet, but we help our clients to get there. As I said, this is the first series of webinars that we want to present for you. I hope, and the team hopes, that you have enjoyed. Certainly, I would like to thank Anja for this crazy interesting presentation, but also how that relates to our daily work together with clients and in between us. I would also like to thank Rasmus Kruse and Emil Prien for helping out and setting this webinar up. So we are a bit ahead of time. Rasmus, are there any further questions?
We have a question for Anja regarding
yes.
If it's possible to hack a satellite, and then there was something about are we alone in space? But I think one of the more interesting ones was actually, what about, we always talk about life as we know it. What about life we don't know? And,
yes.
And how can we get more certain on what's out there?
So yes, it's possible to hack a satellite. So that's why there's so much security around it. It's not possible to do what you see in spy movies where they zoom in, do, and then you can read people's number plate or something. No satellites that. So even the James Webb 6.5 meter telescope wouldn't be able to see that resolution on Earth because of the Earth atmosphere, right? I mean, you're looking through this haze, so don't believe everything you see in movies. And life as we know it, so that is the big problem, is that we can actually imagine that life would be different. So we are what we think of as a carbon-based life form. So we consist of carbon atoms, but anything which is in the same part of the periodic table, and you probably don't remember, but beneath carbon there's silicon. And silicon actually chemically has all the same properties as carbon. So we believe that there might be silicon-based life form. And a computer is somehow a good example of a silicon-based life form to some extent, because it also somehow illustrates what carbon can do and silicon cannot do. Carbon can make very flexible bonds, so that's why I can do like this. And silicon makes very stiff bonds, which is why my computer is. So you would expect sort of different movements just because of and that's what I find is so fascinating, is so the little atoms and the way that they bond to each other actually is going to dictate the big movement of. So something C3PO or R2D2 like you could imagine, right? So the reason that we look for liquid water is because that's an easy question to answer, right? Is there liquid water or not? We know what liquid water looks like. And then once we have found water or we found oxygen in an atmosphere, then we need to ask the difficult question, which is there life? And is there life as we know it, or is there a different type of life, right? Because life on Earth can even be very, very different. So we can even have a hard time recognizing life forms on Earth, which are, even though we share like 80% of our DNA with all life form on Earth, right? I don't know if you talked to a banana recently, but we are quite genetically like a banana, right? So yes, there's life. It could be very different. It could be so different that we wouldn't even recognize it, even if we're standing next to it. And that's one of the big challenges. But challenges is what is interesting, right? Because then you just got to keep asking questions, thinking, that's exciting. You know, it's difficult, it's challenging. Let's see if we can solve it. I don't remember what the last question was.
I think one of the other questions was about how much have space exploration or astronomy and so learned from IT or in the tech world?
I mean,
are we using AI and robotics?
Yeah, so there's no doubt that astronomy, I mean, it's a very old science. So people have been doing it for like several thousand years, just using the eye. But the discovery of the telescope by Galileo, who was the first one, and later this discovery of electronics. So instead of photographic plates, you could actually use little CCDs that we now have in our mobile phones, has actually accelerated astronomy immensely. And the better technology we get, as I try to illustrate with the adaptive optics, so we are somehow very technology driven. So every time there's a new tech discovery or there's a new engineering project going on that can give us new facilities. And since astronomy is so exciting, we also go the other way, where we go out to tech people and engineers and say, we would like an instrument that could do this because we want to see this. And they're like, oh, looking at black holes, that sounds really exciting. Let's see if I can help you out discover something. So I think that the big picture of looking into the sky and trying to understand our place in the universe, even though it might seem a bit like a waste of time because we can never reach the stars, I think it's very inspirational for actually developing tools so we can get more answers and tools, which are then very useful for a lot of other things. So I think the internet is also a good example, right? That was some particle physicists who want to share data on how particles became smaller particles when they bumped into each other. And I think if those physicists had realized that once they start sharing data in the fashion they did, we would get the internet with all the excitement and problems of the internet with social media and share of pornography and God knows what. But it's definitely changed society, right? It's been a big thing and nobody saw it coming. Nobody could predict it. There's no sci-fi movies before the internet that predicts the internet. And that's interesting, right? Because sci-fi movies are actually quite imaginative, but it's always something like a 3D thing on a little chip or something. It's not the internet.
I love that we hopefully can steal your bright mind to coming sessions. And I think you already mentioned some of the potential topics around other life and a lot of other great.
I'll be very happy to come back and talk about whatever people would like to hear.
Thank you very much for your time, and to all the people listening in. Thank you.
Yes, thank you so much again. And just a little disclaimer, I mean, 7N is proud to work with the best, and now also you, Anja. So have a nice evening and see you soon again.
Thank you for listening in.